Okay, let's start working some videos and some additional practice for you guys. Again, on the first slide of the additional practice, you will, if needed, like if it's helpful for the chapter, um, you will find something that looks like this. These may be used throughout the examples in the question. If something else is needed, it would probably be given to you. Not everything is given to you in additional practice. On exams or quizzes, exams especially, this information would be provided on the first page of the exam, on the cover page. On a quiz, it would probably be provided at the very top of the quiz if it wasn't in the question itself. But I will try to emphasize like when you need this information and why as we go through to help train you guys as you're going through, okay? So first up, let's do question one. Try to zoom in here. What is the freezing point of a 4.0 molar NaOH aqueous solution with a density of 1.04 grams per ml? Okay, so there's a few things going on here. First, we are given molarity and we're looking for freezing point. We know it's an aqueous solution, so we know what our solvent is, and we're given a density. So, because I need colors I actually like to write with. Okay, what kind of things in here are important? Well, what I'm trying to find freezing point. I should probably use a color that doesn't blend for you. Okay, we're trying to find freezing point. We know that it's a 4 molar sodium hydroxide solution. Okay, so that's telling me something. We also know it's aqueous. Remember, aqueous means that water is my solvent. And it's got the solution itself has a density of 1.04 grams per mil. There are times where I'm going to give you questions with just extraneous information. This is not one of them. This information is actually useful. Let's think about what all these things mean. First, if I am looking for freezing point, I know my equation for freezing point is delta TF equals KF times lowercase m times I. What do those things mean? KF is your freezing point constant. The lowercase m is your molality, and I is your Van Hoff factor. Okay? So you got to keep that in mind. We do not have molality listed. We have molarity. So we're going to have to do something to figure out what our molality is. Our KF value for water, KF value in general is a constant, but we're given it for water on the previous slide. So we have the KF value for water. And we're going to, because it doesn't say otherwise, we're going to use the idealized Van Hoff factor for sodium hydroxide. Okay, so let's go ahead first. So we know that the KF is equal to, and I never remember this constant, you could have given it, 1.86 degrees C per mol. Okay, my I value, my Van Hoff factor, again, what does sodium hydroxide split up into when it's in solution? It splits up into two things, sodium ions and hydroxide ions. So if I had 1 mole of sodium hydroxide, I would have overall 2 moles of ions, so my Van Hoff factor is a 2. And what I really need to find is that freezing point, but first I need to figure out that molality. So how are we going to do that? We need to go from molarity to molality to figure out this problem. I know that I have a 4 molar solution. What that means is that I have 4 moles of NaOH for every 1 liter of solution. But again, your solution is your solvent plus your solute. For molality, for this, molality is equal to number of moles of solute divided by kilograms of solvent. So I've got to separate that out somehow. How am I going to do that? Well, I don't know how much solution I have. It didn't tell me. Which actually makes the question easier, though. Because it didn't tell me how much solution I have, I'm going to go ahead and assume that I have a 1 liter solution. That made my life a lot easier because that means that I have 4 moles of NaOH. If I have a 1 liter solution and I know the density of the solution, 1 liter, I know there's 1,000 mils in every 1 liter, but I know my solution is 1.04 grams per 1 mil. So I have a 1.04 kilogram solution. Cool. I know how much my solution weighs. I can pretty quickly figure out how much my solute weighs because I know I have 4 moles of it. 4 moles of sodium hydroxide. Convert that over. Sodium hydroxide has a molar mass of 40 grams per mole. Gives me 160 grams of sodium hydroxide if I had a 4 molar solution. So I know two sig figs, by the way. Two sig figs are here. That 0 is not significant. Two sig figs in this question because of the 4.0 here. So I know I have 0.16 kilograms of sodium hydroxide. 1.04 kilograms of solution. I apologize about my writing. My wrist is really sore and I'm doing my best here for you guys. 0.16 kilograms of solvent gives me 0.88 of the solvent. Why do I care? Because I can use that to find the molality. Let's find a color that we can actually see. I know my moles of solute. I'm assuming that I have that 1 liter solution, so I know I have 4 moles of solute. I now know how many kilograms of solvent I have, so now I can find that molality. I have 4.0, oops, I apologize, 4.0 moles of NaOH. I have 0.88 kilograms of solvent, which gives me a 4.5 molal solution. Now that I have that, I can finally use the goal of the whole question, which is the equation here. And I'm going to go over to the other side of the screen. Okay, so my delta TF is equal to 1.86 degrees C per molal times 4.5 molal times my Van Hoff factor, which is 2. When I calculate all that out, I get a value of 16.9. What is that really? What are my units here? Let's see. My molality has canceled. Van Hoff factor doesn't have a unit. I've got degrees C, which is good. This should be a change in temperature. So I get 16.9 degrees C. Remember your sig figs, though. You have two sig figs. So 2 sig figs. So this gives me 17 degrees C. Is that my final answer, though? No, that's not my final answer at all. This is just the change in freezing point. I have to remember what temperature water freezes at. Water freezes at 0 degrees Celsius. Freezing point depression means that it got even colder. So therefore, my actual freezing point is going to be negative 17 degrees C for this question. Okay, so I'm going to write that over here. I'm going to shrink this stuff down. I guess you can just pause the video, but I'm going to try to shrink this stuff down to not lose it on the screen. Move this over. But you figured out the first one. Good job. So we've got one down. Are you guys ready for question 2? See what it says. How much ethylene glycol, C2H6O2, in grams must be added to 1 kilogram of water to produce a solution that boils at 105 degrees C? Okay, so you'd have to know here that ethylene glycol is a non-electrolyte. And truthfully, the best indication of that is what it's made of. It's made of just nonmetals. And it's not a polyatomic I have memorized. It's not an ionic compound. It's just made of nonmetals. Your molecular compounds, meaning they're just made of nonmetals, and they're not your polyatomic, so they don't have a charge to them. It's not like phosphate or nitrate or ammonium, nothing like that. They're just non-electrolytes. They're not going to break up into multiple things in solution. They're going to stay one particle. But what that also means is that my Van Hoff factor is equal to 1. I'm looking here. I'm trying to find how much ethylene glycol. How much? This is telling me I need grams. It then says must be added to 1 kilogram of water, so I know how much I'm using of solvent, to produce a solution that boils at 105 degrees C. So I'm looking at delta T B, which is the change in boiling point temperature, is equal to KB, which is the boiling point elevation constant, times the molality times I. Okay? I know one of the things I will not give you the boiling point or freezing point for water. You need to know those. Okay? Anything else, if it wasn't water, I would give it to you because you wouldn't know them. But water, you should know that water boils at 100 degrees Celsius. Therefore, if I'm boiling something at 105, my delta TB has to be 5 degrees C. I also can look up my value, and if you need to write that out, that's fine. It's just, the 105.0 degrees C minus 100 degrees C. Don't let this one limit your sig figs because that's 100. It can go out to any decimal place you want. Let this limit your sig figs here, and that's where I got the 5.0. So again, this is what gave me this here. My KB value is a constant, 0.512 degrees C per molal, times my molality, times my I value of 1. So I'm going to solve here. I'm going to rearrange this equation algebraically and solve for that molality. My molality is equal to 5.0 degrees C divided by 0.512 degrees C per molal times 1. My degrees C have canceled out. This is leaving me with units of molality, which is good because that's what I expect to see. And I have my answer here is 9.77 molal. Now, that's not the answer to the question, but it's the first part of the question I need. What that means is for the solution itself, I need 9.77 molal to get an ethylene glycol solution to raise the boiling point by 5 degrees C. The question also told me, I apologize, the question also told me I have 1 kilogram of water. I can use that information along with my molality to quickly find out how many moles of solute I need. So if I have a 9.77 molal solution is 9.77 moles of C2H6O2 in 1 kilogram of solvent, and I'm told I'm using 1 kilogram of solvent, because again, water's my solvent. This means I have 9.77 moles of my solute, which is at C2H6O2. I'm going to use that value, the 9.77 moles of the solute, and convert with its molar mass to grams. So if I have 9.77 moles C2H6O2, its molar mass is 62.07 grams per 1 mole. This means I would need to add 610 sig figs here to keep, or decimal place here to keep my sig figs in place, grams of C2. Oh, hold on a second. Actually, I said that wrong. My sig figs. I had 2 sig figs here. So 2 sig figs here, 2 sig figs here, 2 sig figs, 2 sig figs. So 610, no decimal place. I apologize. Grams C2H6O2. I need 2 sig figs in my final answer. And that's why I'm writing it to 610, not putting either another number there or a decimal place there. So, how much ethylene glycol is going to need to be added to 1 kilogram of water to produce a solution that boils 105 degrees C? 610 grams. Fair amount of ethylene glycol. I recommend a different thing if you're trying to get that thing to boil. Enough commentary. Let's look at number 3. Calculate the freezing point of a 0.89 molal solution, aqueous solution of calcium chloride. So again, let's break the question down. I want freezing point. That means I need delta TF equals KF times M times I. I have a 0.89 molal aqueous solution. What that means is I have 0.89 moles of my solute, which is calcium chloride, in 1 kilogram of solvent, but my solvent is water because it says it's aqueous. And because I have calcium chloride, I know that CaCl2, that means my I value is a value of 3. Because calcium chloride splits up into calcium ions and 2 moles of chloride ions. And yes, you have to specify that they are ions. They are not the regular thing anymore. Calcium and calcium ion are not the same thing. Chlorine and chloride ion are not the same thing. So you make sure to include the charges when you're writing these things out, okay? Delta TF equals KF, which is a constant, 1.86 degrees C per molal for water, times my molality, which I was given in the question, 0.89 molal, times the Van Hoff factor of 3, because again, it's calcium chloride, and this gives me 4.97 degrees C. Now let's check my sig figs before I finish the question. 2 sig figs, which means my final answer here needs 2, so 4.97 becomes 5.0 degrees C. But again, that is not my final answer. That's just the change in temperature. It is freezing point depression, which means the freezing point must decrease or depress. It has to go down, which means for the solution, because it's aqueous, I'm starting at 0 degrees C and I'm going down. My freezing point is negative 5.0 for sig figs degrees C. Let's look at number 4. A solution of ammonia is made by dissolving 35 grams of NH3 and 90 grams of H2O. If you don't know the formula of ammonia yet, you should probably learn it pretty quickly. The density of the solution is 0.898 grams per, I don't even know why that says Mr. That should definitely be mils. Didn't realize that. What is the molarity of sodium hydroxide? I'm doing great. What is the molarity of ammonia? Definitely in ammonia. Sorry, you guys. Okay, let's see. Let's go back. What do we got? We got 35 grams of ammonia. Okay. Got 90 grams of water. Okay. I've got a density of the solution. Okay. And I want molarity. So what I want is number of moles of NH3 for every liter of solution. I know what went into making the solution, so I can figure, and I know how many, I know that water is going to be my solvent and ammonia is going to be my solute. Why do I know that? Well, water is present in a greater amount. I'm making a solution of ammonia. By making a solution of ammonia, that's implying ammonia is my solute. Plus ammonia is a gas. It's going to go into water and make ammonium hydroxide in solution. So I don't care where you start. Let's just figure out the moles of ammonia first. Seems easiest to me. If I have 35 grams of NH3, 1 mole of NH3 is 17.03 grams, and this gives me 2.05 moles of NH3. So I've got my numerator. What I need now is that liters of solution. If I look, it tells me my total solution is 35 grams of ammonia and 90 grams of water. Again, that's up here. 35 and 90, okay? When I add those together, I'm doing addition at this point, so my sig figs go by decimal places, or that's, I have to be careful how I say that. In this case, it's not actually decimal place. It goes by precision in the measurement. And this is least precise. So my answer when added together is 125 grams of solution. But I have the density. So number of liters of solution, that's an equal sign, is 125 grams. I know 1 mil is 0.898 grams. I know 1 liter is 1,000 mils. Gives me 0.139 liters of solution. 14.7 molar, but I need two sig figs. 'Cause again, my sig figs are right here. Or sorry, that's three sig figs. Where did I get to do? 35. I should really start marking these. I'm sorry, you guys. Two sig figs overall to my answer. 15 molar NH3 in this solution. So if I mix the solution up by mixing up 35 grams of ammonia with 90 grams of water, as long as I know the density of that solution, I can find the molarity. And the molarity of that specific solution would be 15 molar ammonia. How about the next one? Which aqueous solution, 1 molal of hydrocyanic acid or 1 molal of sodium cyanide, would have a higher freezing point? Fully explain your answer. Okay, I'm not going to write this because, again, my wrist really hurts. And I'm going to write as little as I can. So you're going to have to listen to this one, okay? I want you to think about what hydrocyanic is. What is the formula of hydrocyanic acid? Hydroic means that it came from a polyatomic that ended in the word "ide." So it came from cyanide. The formula of cyanide is Cn minus. That means hydrocyanic acid is HCN. It is an acid, which means that it will lose a proton in solution. It'll be deprotonated, okay? But it's not one of the 7 strong acids I have memorized, which means it is a weak acid, which means it will partially dissociate. How much? We're going to study that very soon. That's coming very, very soon, but not quite here yet. But it means that it will partially ionize in solution. Some of it will break apart, but not all of it. If I have, so the Van Hoff factor, the I value there is going to be greater than 1, but it's going to be less than 2 because not every single particle is going to split up into a proton and the cyanide ion. On the other hand, if I have sodium cyanide, which is NaCN, that will split up into sodium ions and cyanide ions. And if we assume complete dissociation, all sodium salts, sodium is a group 1 metal, so all sodium salts are 100% soluble, meaning that they completely dissociate in solution. So the sodium cyanide will have an expected or calculated value for the Van Hoff factor of 2, compared to the hydrocyanic acid having 1 point something. That means that the sodium cyanide will have more particles in solution. Okay? More particles cause the solution to have a lower freezing point because you got to make it cold. There, remember, those particles are disrupting the crystal structure of whatever you're trying to form. In this case, most likely, or this case, yes, water in aqueous solution. So water freezes by cooling down those particles enough that the hydrogen bonds take over and lock it into its solid structure. The sodium cyanide has more particles there, more particles present, disrupting that structure. So therefore, it's going to have to be even colder to cool it down enough to let the solution actually freeze, which means to have the higher freezing point, I'd have to pick the species that has the fewer particles because the higher freezing point means I didn't have to go as cold to freeze the solution. I hope that makes sense. If it doesn't, well, come see me. Number 6. What is the vapor pressure of a solution formed by mixing 6 moles of methanol with 8 moles of propanol at 40 degrees C? Okay, I don't know. 40 degrees C, the vapor pressures of pure methanol and pure propanol are 303 and 44.6 torr respectively. Assume this behaves in an ideal solution. So this is a combination. This is an application of Raoult's law. In class, we did ones where only one of them was volatile. In this case, they both happen to be volatile. That's fine. The math works the same. I know I have 6 moles of methanol, and the pressure is 303 torr. So 6 moles of methanol, 303 torr, and I have 8 moles of propanol with a partial pressure of 44 torr. Raoult's law tells me that the total pressure of the system is going to be equal to the mole fraction of methanol, this is the abbreviation for methanol, times the partial pressure of methanol, pure, plus the mole fraction of propanol, times the pure vapor pressure of propanol. Again, PROP standing for propanol. I just got to figure out those pieces. I know that the pure pressure of methanol is 303 torr. I know the pure vapor pressure of propanol is 44.6 torr. So I just need to figure out the pieces that are missing, which is the mole fractions, which is pretty easy on this one because it already gave me moles. So that was nice. The mole fraction of methanol is 6.00 moles of methanol over the total moles of the system. Because again, mole fraction is how much do I have of one versus the whole system. 6.00 moles plus 8.00 moles is 14 moles total. This gives me 0.429 for the mole fraction of methanol. Can do the same thing for propanol. Eight moles of propanol divided by 14 moles total gives me 0.571. What does that mean though? That means that 57% of my sample is due to propanol and 43% of my sample is due to methanol. That's what the mole fraction is telling me, right? It's just doing it in fractional form. But that means that 43% of the pressure from the system is coming from the methanol, and the other 57% of the pressure of the total system is coming from the propanol. Multiply them together, and my total pressure here is 155 torr. So hopefully that seems pretty straightforward to you guys. It's very similar to what you guys learned in Chem 1 under the gas laws chapter. Number 7, 6.40 grams of an unknown solid are dissolved in 100 grams of benzene, which has a boiling point of 81.7 degrees C. What is the molecular mass of this non-volatile, non-electrolyte solute? Well, let's break it down. I've got 6.4 grams of an unknown solid. Okay, I'm going to need that because if I'm trying to find molar mass, I know molar mass. I don't want to ask Siri anything. I know molar mass is grams over moles. So 6.04 grams of my unknown, I need to figure out the moles of the unknown. If I can figure that out, I can figure out its molar mass. It's dissolved in 100 grams of benzene, gives me the formula of benzene, which has a boiling point of 81.7 degrees C. I want to know the molecular mass or molar mass, whatever you want to call it, of this non-volatile non-electrolyte. Okay. When dissolved, it has this boiling point, which means this is the boiling point of the solution, which means I need to look up the boiling point of benzene. I didn't give it to you in the question because it's a homework question. You can look it up. On the exam, you'd have to recognize you have to look at the first page for that, okay? I wouldn't expect you to know this. The boiling point of pure benzene is 80.1 degrees C. How do I know that this here is the boiling point of the solution? Because it says the solution is added to benzene, and this has the boiling point of this. That's implying it's the whole thing. It also tells me non-volatile, which I don't much care about truthfully, unless it's a vapor pressure thing, then I care. But the non-electrolyte, that part matters. That's telling me that my I value is equal to 1. So I know I'm doing boiling point. So delta TB equals KB times M times I. We know that the solution is 81.7 degrees C. And I looked up the boiling point of benzene. Again, on homework, you guys can look that up. On an exam, I'd put on the very first page, on that cover page, on a quiz, it would be at the top. 81.7 degrees C minus 80 degrees C equals, I'd have to look up that KB value for benzene. And for benzene, it happens to be 2.53 degrees C per molal. You guys can look this up in your books. Times your molality times that Van Hoff factor, which is 1. I get a molality here, 0.632 molal, and it does have two sig figs. It specifically has two sig figs because when I do the subtraction here, I'm going to be left with two sig figs, 1.6. So I've got two sig figs, okay? Not going to write it down as two yet. I'm going to keep it where it's at, but you do need to recognize it's two sig figs. It tells me that I have 100 grams of benzene here. 100 grams of benzene is 0.100 kilograms of benzene. But that means I can use that information to find the moles, because I can use this information right here to find the moles of solute. I know my molality means I have 0.632 moles of my unknown for every 1 kilogram of benzene. Multiply that by my 0.1 kilograms of benzene, and I have 0.0632 moles. Again, my sig figs are at the 2, but I'm just going to carry an extra one right now just for safety. Common question from students, how many sig figs extra do I carry? I usually carry one until the very end. That tells me that I have this many moles. I'm going to plug that into the equation up here. Sorry, I'm trying to get them all on the same screen. 0.0632 moles of my unknown, which gives me 101 grams per mole. But I need to round to two sig figs. So 100 grams per mole. That's annoying. I need two sig figs. I have to use scientific notation. 1.0 times 10 to the second grams per mole. Now I have to use scientific notation. Not my favorite thing. Okay. What does this really mean though? Like, does this question make sense to me? What this means is when I added just 6.4 grams of this unknown to benzene, the boiling point was elevated by 1.6 degrees. Okay. So when I did the math here to find the molality, knowing that I only had 100 grams of benzene, that means that I had to have 0.032 moles of that unknown solute in there to cause that boiling point elevation. So that's how I'm able to say these grams to this moles. Mathematically, the system is telling me, based on the experimental results we saw, this had to be the number of moles present. Again, moles tell me the number of particles that were present in the reaction. So I had to have that many moles present, and I already knew the grams, so I'd measured it separately, and so therefore I can easily find the molar mass. I did write all over the place. Pause it if you need it. I'm going to erase it because I want my board back. What about the next one? What are we doing here? A solution of hydrogen peroxide is 30% hydrogen peroxide by mass and has a density of 1.110 grams. What is the molarity of the solution and what is the molality of the solution? Okay. So we've got hydrogen peroxide, which is H2O2, and we know it's 30% by mass. We have a density of 1.11 grams per mil, and the two things we're trying to find is molarity and molality. Let's do it. When you are given a percentage, especially percentage by mass, I want you to assume 100 grams of solution. Why? Because this makes your math really easy. If I have 100 grams of solution, that means I have 30 grams of H2O2 per 100 mils. Sorry, by mass means grams. 100 grams of solution. That also means I have 30 grams of solute and 70 grams of solvent. Is it for sure water? I don't know. Let's just write solvent. I'm assuming it's water. Doesn't tell me though, and it doesn't truly matter. But because it says by mass, that means percent by mass means it's mass of one to mass of the other, mass of the total solution. So if I have 30 grams of peroxide, I've got 70 grams of solvent here. That makes the molality really easy to calculate. Because again, molality, number of moles of peroxide divided by my kilograms of my solvent. Peroxide, 30 grams, 1 mole of H2O2, 34.02 grams. H2O2 gives me 0.882 moles, 3 sig figs here, 3 sig figs here, of H2O2. $70 grams, 0.0700 kilograms. Move this over. That gives me a molality of 12.6 molal. So that one was really easy to do. Let's look at the molarity one. What do I mean by molarity? Molarity is number of moles of solute, which I already know to be 0.882 moles. Per liter of solution. I don't know the liter of solution, but I can use the density to find it. Because I assumed 100 grams of solution, number of liters of solution, 100 grams. Don't let that 100 limit your sig figs, by the way. Let your density do it, okay? Because you can put that decimal place wherever you want on this. Truthfully, you should probably write 100.0 because you did 30.0 here. I know that I have 1 mil for every 1.11 grams of solution. I know that there's 1 liter for every 1,000 mils. This gives me 0.0901 liters of solution, which gives me a molarity here of 9.79 molar. And don't forget, molarity is that capital M, molality is that lowercase m. What number 9? What is the mole fraction of sucrose? C2H12O11, or sorry, C12H22O11. I don't know what I just said. If 25 grams of sucrose is dissolved in 165 grams of water. So I want the mole fraction. What is mole fraction? Mole fraction of sucrose is the moles of sucrose divided by the total moles of the solution. Let's find the moles of each thing. Number of moles of sucrose at 25 grams. One mole. That's pretty big. 342.3 grams. Gives me 0.0730. Need 3 sig figs, so that's why I got to carry that extra 0 moles of sucrose. Extra 2 up there. So 0.0730 moles. I'm going to stop writing that formula for sucrose right now because that's a lot. I'm going to write SUC for sucrose. That was faster. Okay, number of moles of water. I've got 165 grams of water. I know 1 mole of water weighs 18.02 grams. This gives me 9.15 moles of my water. So my mole fraction of sucrose is pretty dang small. 0.00791. What does that mean? It means that less than 1% of the solution is actually due to sucrose. The rest is due to water. Not a lot of sucrose in there. If you need this, please pause the video and write it down because I'm about to erase all of that for you. Number 10. How many grams of methanol must be dissolved in 2.50 times 10 to the second mils of water to produce a 0.325 mol solution? So the density of water is 1 gram per mil. 2.5 times 10 to the second mils is annoying to me. It's only written like that, just to be annoying. I'm convinced of that. That and it keeps your sig figs, but I don't want to deal with it. So let's just write that the right way. 250 with a decimal. With that decimal place, it now has 3 sig figs. And now I have to look at scientific notation. Makes me feel better. Okay, I have that many mils of water. I want a 0.325 ml solution, and I've got the density. Okay. What am I trying to find? I forgot. How many grams of methanol? Sorry, I really do apologize, you guys. I'm tired and my brain is not focused. I'm trying to find grams of methanol. I know I have this much water. I need this concentration. I've got this density. Okay, let's do it. Well, I know that if I have 250 mils of water, my density is 1 gram per mil, so it's a 1-to-1 ratio, which means that you can look at the work that's posted if you want to in the key that's posted online, but this would be 0.250 kilograms of water. Again, if you need to see that written out, please go look at the key that is posted in your online system. But because of the density there, it's a 1-to-1 ratio, and so I've got 0.25 kilograms of water. My grams of methanol, I've got 0.325 moles of methanol for every 1 kilogram of water. Where did I get that? Right there. That's what I'm trying to find. That's what I need, right? So I know I've got that, and I know I've got 250 mils of water, which is 0.250 kilograms. So times 0.250 kilograms of water. If I stopped right here, this would give me the moles of methanol I need. But I don't really want moles. I want grams. Can't measure moles out. 32.04 grams of methanol to every 1 mole of methanol. I need 2.60 grams of methanol to make this solution. And to be completely honest with you, methanol comes as a liquid. So truthfully, the question should even just ask you for mils and give you density of methanol as well. But as written, this is how you would solve it. Okay, let's go ahead and look at example 11. Students don't like this example, and I get it. It's a little complex in its thinking, but hopefully I can take you through it and you can understand it and understand how and why we're solving it. Because if you can do this kind of example, it doesn't get much more strange than this, I would say, unless you're converting between different things. Like, what I mean by that is like freezing point to boiling point or something like that. Let's go ahead and think our way through this example. We have a metal, M, that has an atomic mass of 96 AMU. Right away, I know what metal that is because I can look at the periodic table and I see that 96, and I know that that is molybdenum. It's reacting with fluorine, like that's cool. We've got some fluorine in here to form a salt that can be represented as MFX. Okay, I know a general formula, like I know I've got the metal complexing with fluorine. The problem is that that little X means I don't know how many fluorine I have, but I know I've got some fluorine. In order to determine that value of X, okay, so that's my goal. I want to find that. And therefore, the formula of the overall salt. Okay, need to do that. A boiling point elevation experiment is performed. Okay, so I know I'm doing boiling point. So I know I've got delta TB equals KB times M times I. I know, okay, what's the next sentence? A 9.18 gram sample. So I've got 9.18 grams of the salt is dissolved in 100 grams of water. Okay, so it's aqueous. My salt is my solute. My water is my solvent. And the boiling point of the solution is found to be 374.38 Kelvin. Okay, I'll talk about that in just a sec. Find the formula of the salt. So I'm trying to find the formula of the salt. Okay. assuming complete dissociation of the salt in the solution. Great. I don't know what my I value is because I don't know what my formula is. But that means that my I value is something greater than 1. I don't know what, but I know it's greater than 1 because I know I have at least 2 things here. I know I at least have metal and fluorine here in this form, fluoride. And so therefore, I know it's at least 2. I don't know what it is, but I know it's at least a value of 2. What else do I know that's not listed? I know I can look up the value of Kb for water. I know that the value for Kb for water is 0.512, I believe. I do actually have to look this one up because I never remember it. And it will be provided for you. Yes, 0.512 degrees C per molal is the units on this. That's how you have to have the units so that it cancels out and gets you the correct things, whether it be temperature, morality, whatever. I do not know my molality. Trying to find that because I know how much grams of solute I have. I don't know what my solute is, so I can't find its moles. I do know my grams of solvent, though, which will be helpful in a minute. And I know my I value is something greater than 1. Okay, how am I going to go about this? 1 second. Okay, I am going to basically put a placeholder in for my I value. There are 2 different ways to solve this problem, I will be honest. And the one way to solve the problem is just by trial and error. Go through the problem. Say if I have MF, I would know the formula, I would know the molar mass, I could find the molality. I know I is equal to 2, I would solve for delta TB and see if it matches. If I had MF2, I could solve for the molar mass of the moles of sample. I could know the I value, could plug it in, see if delta TB matches. If I had MOF3, etc. I could keep going until it matches, but that's kind of time consuming a trial and error experiment when I could just solve the question. Okay, and that's what we're going to do today is we're just going to solve the question. We know that I is equal to our one metal plus some number of fluorines. I don't know what the number is yet, but I know that I is equal to the 2 combined. And that's what I'm going to use algebraically to solve the question. Another thing I know is I know my delta TB. I know that the temperature that a solution actually boiled at was 374.38 Kelvin. But I know water itself boils at 100 degrees C. And remember when you write 100 like this could be as many decimal places as you want. So let's just do it out so you can see the sig figs here. If I want to convert this to Kelvin, I would add this to 273.15. That gives me a boiling point of 373.15 Kelvin. So I actually know my change in temperature here. 374.38 Kelvin minus 373.15 Kelvin gives me 1.23 Kelvin. But when it's the difference in temperature like that, because Kelvin is just a linear scale, that means it's also equal to 1.23 degrees Celsius. Okay? So at this point, I know this, I know this, and I have a placeholder for this. Not the best, like people don't like it, but it will work. Let me show you. I know I've got 1.23 degrees C, my delta T B, because it's boiling point. I know it's 0.512 degrees C per molal for my Kb, because it's water. I have no idea what my molality is. That's what I'm trying to find. And I know that my I value is going to be equal to 1 plus x. When I solve this through, I'm going to divide both sides by that 0.152 or 0.512 degrees C per molal first. That's going to give me 2.40 molal is equal to the molality times 1 plus x. And then I just divide both sides by 1 plus x as well. Why? I'm isolating the molality. What this tells me is my molality of the solution is equal to 2.40 molar, or molal, 1 plus x. Now, it's not a pretty number, but you've solved questions like this before. This is usually what you do. It's just usually a single number. This is when you take this, we know the molality is equal to the mole over the kilograms. We could take this, multiply that by the kilograms of solvent, and usually solve the question. This just looks a little ugly because of that 1 minus x in the denominator, but we're not going to let it trip us up. We are going to erase some or move some things because I don't have space. Because that question's a big question. Okay. So what I mean by that again is that value down there, that 2.40, that means I have 2.40 moles of my solute, or you could write MOFX, whichever one you prefer, I don't really care, over 1 kilogram of solvent, and that whole thing has that, I keep writing minus, 1 plus x in the denominator. That's my molality. The question told me that I had 100 grams of solvent in here. So that means I can take this and multiply it by 0.100, how many sig figs there for? 0 kilograms of solvent. This gives me 0.240 moles of that MOFX or MFX, whatever you want to write at this point. Solute, whatever, I don't care, it's placeholder, divided by 1 plus x. It's still ugly, I'm not denying that. But normally you just have a value there of moles, right? Now we've just got that 1 plus x kind of hanging on because we're still trying to figure out what it is. We really don't have enough room on this slide. So again, this is my moles. What that means, remember when you're solving molar mass, it's always grams over moles? Same thing here. I know I had, what did I have? 9.18? Yep, 9.18 grams of the MOFX. And I know my moles is 0.240 moles of MOFX divided by that 1 plus x. I don't know why, but writing 1 plus x is really difficult. Okay, try not to let that color blend in too much right there. I should have used a different color. Just kind of separating it right there. Still need to solve that thing. How am I going to do that? Well, I'm going to use molybdenum to help solve this question. I know that molybdenum weighs 96 AMU. Why? It told me. I know that the F is how many fluorines I have. I just don't know how many I have. So I'm going to set this equal to 96 for the molybdenum plus 19x for the fluorine grams over 1 mole of MOFX. Why is that going to work? Well, because if this is the molar mass, this is also the molar mass. These two things are equal to each other. The number of this, remember, this here is scaling it. So if I only have this many grams of the entire thing, then I only have a certain number of moles of that entire thing. But the true compound, if I had an entire mole of it, would have this formula. Again, I don't know how many I don't know how many x's there are, but I know that 96 plus 19 times that number of x's would equal 1 mole of that compound. And I'm going to algebraically solve this thing. I don't know where I'm going to do this. Let's find some space. Excuse me. We're going to erase, so please write down things you're missing. So to algebraically solve that, I've got this thing up here that I'm going to be solving. Okay. I'm going to simplify this. 9.18 grams times 1 mole of MOFX. This is 9.18 grams of MOFX. So basically, I took this and multiplied it up. Do the same thing on the other side and take this and multiply it up that way to clear out the denominator. This is equal to 96 plus 19x grams of the MOFX times 0.240 moles of MOFX. I'm running out of space really badly here. Divided by that 1 plus x. I need to stop writing a minus sign there. It's definitely a plus x down there. I apologize. I'm going to try to solve this algebraically. Now it's not so bad. So you're distributing through. So on this side of the equation, I get 9.18 plus, um, hold on, I flipped my things around. Let me make sure I'm matching what your screen says. Ah, algebraically, I need to actually, because I know some people need that, that's fine. I'm multiply through both sides of the equation by this. So I'm going to say times 1 plus x, and then times 1 plus x over here. 1. I have the hardest time writing that plus after that. Okay, that cancels that out, brings me the 1 plus x over here. So now what I have, I'm going to drop the unit, or the labels right now. I'm just going to put the units. I have 9.18 times 1 mole times 1 plus x is equal to 196 plus 19x, and that's grams, times 0.240 moles. Okay, so all I did at that point was multiply both sides by the 1 plus x to get that out of the denominator as well. Now I'm going to distribute. The 9.18 times 1 mole stays 9.18, but I need to distribute this quantity into here. That gives me 9.18. Let's see, plus 9.18x. For here, I need to distribute as well. I'm not going to mess with the units right now. They're going to cancel out in a sec anyway, and they're just getting messy in my space. Distribute this through this direction. This is going to give me 23.04 plus 4.56x. Now my sig figs here would be here and here. My sig figs here are here and here. Not that it's going to matter. We're going to calculate an I value, and the eventual formula is going to be a whole number, but just in case you are trying to track your sig figs. Isolate your x. I don't care how you do that, but you should do that. I like putting all of my x's on one side, and then I like making them positive. That's what I'm going to do. I've got 4.62x was 13.86. So basically what I did was I brought all of my x's to that side, my non-x's to that side. Okay. 9.18 minus 4.56. X gave me this. 23.04 minus 9.18 gave me this. Now I can solve for x. X is, let's see, 13.86 divided by 4.62 gives me a value of 3. It's a lot of work. We haven't quite solved it. Almost there. What does that actually mean? My x, so I can find a color that we haven't used yet, which is highly unlikely. My x value down here of 3, way back up here, we said that that x value represented the number of fluorines in the sample. I know it's been a bit. It's been a kind of a probably a long point of the video at this point. But what that means is that my formula is MOF3. I have 3 fluorines for every 1 molybdenum based on the way the question solves out. So again, I'm able to do that because I don't know what that I value is initially, but I know that I have 1 molybdenum. So when it's added to that I value, the number of fluorines added to the I value have to equal I. And so I kind of held it off solving it algebraically all the way until the end. Now I need to erase all of this. 1 second. Okay. Hopefully you paused it and wrote all that down. Number 12, a 50 ml solution is initially 1.55% magnesium chloride by mass and has a density of 1.05 grams per ml. What is the freezing point of the solution after you add an additional 1.35 grams magnesium chloride? We're going to use a Van Hoff factor 2.5 for the solution. Why would we use a Van Hoff factor 2.5? Well, truthfully, whatever the solution is, just is not acting ideally, so we have a slightly smaller Van Hoff factor. Remember, the Van Hoff factor assumes that the solution is behaving ideally, meaning that the particles are not interacting at all. Truth is, that doesn't usually happen. Usually the particles do have some type of interaction. Therefore, the Van Hoff factor, which assumes all the particles would otherwise act independently, they're not independent, so the Van Hoff factor is actually a little bit smaller. So let's see, I've got a 50 ml solution. That solution contains my solute and my solvent. I know the solution is 1.55% magnesium chloride by mass. That alone tells me assume. Well, no, I can't assume. I know the volume. If I had just that, I would assume 50 mL of solution. Instead, I'm going to use that math and use half of that solution. And I'll show you that in just a sec. It does have a density, which we will need. Density 1.05 grams per ml. That's helpful. That's going to help me get my solution into mass. I want to know freezing point. So I know I'm going to be doing delta TB or delta TF equals KF times M times I after I add additional magnesium chloride. Okay. And I got an I value. Okay. And I know the KF value because I know the KF value for water. It will always be provided. So, all right, let's see. We got 50 ml solution. Let's hear how many grams of solution I have. I've got a 50 milliliter solution. I know the solution is 1.05 grams for every 1 ml. I have a 52.5 gram solution. I know that 1.55% of that solution is actually magnesium chloride. So we taught you how to do this in Chem 1 using percentages as dimensional analysis, and that's what we're going to do here. Number of grams of magnesium chloride. If I have a 52.5 gram solution, I've got 1.55 grams of magnesium chloride for every 100 grams of solution. So I have 0.814 grams of magnesium chloride in my solution initially, and then added some to it. Cool. So my total grams of magnesium chloride will be 0.814 grams plus 1.35 grams. Overall, 2.16, sig figs are here, grams of magnesium chloride. Unfortunately, that's not the answer to the question totally, but it will help. We're getting there. Now we know how many grams of solute we have, and we can figure out how many kilograms of solvent we have, so we can solve the question. I do need to know how many moles, though. Let's convert this to moles. I'm not going to write it out because you guys should know how to do this by now. But if you look up the molar mass or add up the molar mass of magnesium chloride, magnesium is 24.31 grams per mole. Chloride is 35.45 grams per mole. We have two chlorides, so it gives me a molar mass of 95.21 grams per mole. This gives me 0.0227 moles. All right, so you guys can read it. A magnesium chloride. I also need the grams of solvent in the solution because, well, that's how we solve the problem, right? Molality is moles of solute over kilograms of solvent. I know I started with 52.5 grams of solution, and I know initially that solution contained 0.814 grams magnesium chloride. I'm not going to subtract the whole amount because I added that 1.35 grams after the fact, which means I have 51.7 grams of solvent. which gives me 0.0517 kilograms of solvent. Now, let's see, it doesn't technically tell me here that it's aqueous, but we're treating it as aqueous, unless otherwise, if it does not specify, treat it as an aqueous solution. If it's not an aqueous solvent, I would tell you that for sure. Because it doesn't say, I'm going to assume aqueous. My molality here, got my moles there, 0.0227. I've got my kilograms of solvent, 0.0517. That gives me a solution that's 0.439 molal. Now I'm going to plug that in to my temperature change equation. So delta T F is equal to 1.86 degrees C per molal times 4.39 molal, and it told us to use a Van Hoff factor of 2.5. Again, normally magnesium chloride would be 3, but we're already saying this is not going to be under ideal solutions. This here is going to give me a value of 2.04 degrees C. And my freezing point here is negative 2.04 degrees C. Let me check one thing, my sig figs, make sure. Okay, 2.04. I'll talk about that in just a second. I just want to make sure my sig figs. 3 sig figs, 3 sig figs. My I value will not limit my sig figs because that could be a whole number. Just kept it at 3. Yep, okay, so 3 sig figs overall. Remember when you solve that delta TF equation, that is just giving you the change in temperature. It's not giving you its freezing point. Water freezes at 0 degrees C, so I need to subtract this value from 0, and that's how I get my final answer. Number 13, calculate the vapor pressure at 25 degrees C of an aqueous solution that is 5.5% NaCl by mass. Assume complete dissociation of the solute. So, two things here. First, the fact that it says aqueous solution means I know I'm dealing with water. That means water's my solvent. It's also telling me I'm trying to find vapor pressure, and it's telling me 25 degrees C. It's actually quite important that I know that, because I know that now means that I need the vapor pressure of water at 25 degrees C, which happens to be, it's a value you would have to look up, and it happens to be 23.76 torr. The temperature itself is not important in the sense of the calculations I'm going to do, but it is important in the sense that I need to know the temperature so I look up the correct vapor pressure. Remember what vapor pressure is. Vapor pressure is the particles that have escaped into the gas phase, but we're in a vapor phase, not a gas phase. What's the difference there? What I mean by that is water, H2O, let's think about it as H2O, right? Between 0 degrees Celsius and 100 degrees Celsius, we assume H2O to be in the liquid phase. But logically, we know that there is H2O molecules floating around in the air around us, even though we haven't reached boiling. Why is that happening? Because water has a vapor pressure. The water molecules are able to escape and go into the vapor phase. The higher the temperature, the more particles that will escape. So the vapor pressure is definitely temperature dependent. So temperature is important to be able to look up the correct value, but it won't be used in further calculation. We also see that it's NaCl here, and that's important because that tells me my I value. NaCl has an I value of 2. It says assume complete dissociation of the solute, so we're going to assume the Van Hoff factor of a 2 because of the sodium chloride. Now, how am I going to solve this? I am given percent by mass. Percent by mass without a concentration, that means I'm going to assume 100 grams of solution. If I assume 100 grams of solution, then I would have 5.50 grams of the solute, and the remaining 94.5 grams would be water. I need to know this information because I'm going to have to find mole fractions. I'm going to find moles and mole fractions to find the vapor pressure. What I need to really figure out is what fraction of this sample is due to the water molecules, not the ions from the sodium chloride, and then that's the pressure I'm going to have. So let's look at the number of moles I've got. First up, I'm going to do the number of moles of water. I've got 94.5 grams of water. I know that 1 mole of water is 18.02 grams. This gives me 5.29 moles of water. I'm also going to find the number of moles of ions in solution, which is my Na plus and my Cl minus. I know that I have 5.50 grams of NaCl. I know 1 mole of NaCl weighs 58.44 grams. And I know that there's 2 moles of ions for every 1 mole of NaCl because it is splitting up into sodium ions and chloride ions, so 2 different ions. This gives me a value of 0. Sorry, I'm trying to read my own writing. And I had to take photos of these so I could write out the answers without recalculating for you guys. 0.188 moles of ions. So now I'm going to find my mole fraction of water. Mole fraction is the number of moles you have of the species you're looking for, divided by the total moles of the system. So I have 5.29 moles of water. I apologize, I could not read my own writing. That should be a 5.24. Sorry, you guys. I had to take pictures of my stuff so I don't have to recalculate all of this on the video. And I'm trying to zoom in on a little screen on my phone. So, moles of ions. That gives me a mole fraction of 0.965. What does that mean? That means that 96.5% of my sample is due to water. The rest is due to the ions. And those ions are going to hold some of that water back. The equation you're going to use to find the vapor pressure, the pressure of the solution, which is your vapor pressure, is equal to your mole fraction of the species that is volatile times its pure vapor pressure. The overall pressure of this system will be 22.9 torr. 3 sig figs because I have 3 sig figs throughout the example. What about the next one? Sodium hydroxide has a lattice energy of negative 887 kilojoules per mole and a heat of hydration of negative 932 kilojoules per mole. How much solution could be heated by boiling the solution? Sorry, how much solution could be heated to boiling by the heat evolved by the dissolution of 25 grams of sodium hydroxide? There's a lot going on in this question. For the solution, assume a heat capacity of 4 joules per gram degree C, an initial temperature of 25 degrees C, and a boiling point of 100 degrees C, and a density of 1.05 grams per mil. Cool. What do we got? We don't have space. That's what we've got. Okay. Please pause the video and write down what you need from number 13, because I'm definitely erasing that for space. Okay. I know that my delta H of my solution is equal to my delta H of my solute plus my delta H of hydration. I also know that my delta H of solute is equal to negative delta H of my lattice. That is lattice energy. So let's delve back into that. What is lattice energy? Lattice energy is the amount of energy that is released when the ions come together in the gas phase and form that solid. In this case, that's sodium hydroxide. So it's the lattice energy is the energy released when NaOH forms, when the sodium ion and the hydroxide ion comes together and it forms. The delta H of the solute will be opposite of that because delta H of solute is the energy required to break apart the sodium ions from the hydroxide ions. So it's going to be completely the same numerical value, but the opposite sign, and in this case, negative. Um, or sorry, in this case, lattice energy would be negative. This delta H solute will be positive. It's going to take energy to break that stuff apart. So it's going to be the opposite of that. And my delta H solution, I'm going to substitute that in. So I'm going to do that quite literally. And I'm going to substitute, let's move some space. I'm going to substitute that right into my equation. Okay. So now my delta H solution is equal to negative delta H of my lattice plus the delta H of hydration. My delta H of my solution is equal to now positive 887 kilojoules. Again, I expect that value to be positive now because what negative delta H of lattice represents is delta H of the solute, which means the energy to break apart the solute molecules. So positive 887 kilojoules plus the delta H of hydration, which is that solute solvent interaction happening. Hydration is the same as solvation. Solvation is surrounding those ions with the water molecules and those interactions forming. So in this case, my delta H of hydration, negative 932 kilojoules per mole. This gives me overall, this is per mole, this is overall negative 45 kilojoules per mole. So what that means is if I solvate an entire mole, or if I dissolve an entire mole of sodium hydroxide, it's going to release 45 kilojoules of heat. I'm not doing an entire mole though. I'm doing part of a mole. How many moles am I doing? Number of moles of sodium hydroxide. I'm not going to write it out because again, well, to be honest, my hand hurts and I don't feel like writing it out. 25 grams of sodium hydroxide times 1 mole of sodium hydroxide over 40 grams of sodium hydroxide gives me 0.625 moles of NaOH. Okay? If you're unsure what to do for that, come see me in my office hours. Now, what am I gonna, I still haven't answered the question though. The question is, how much solution could be heated to boiling by the heat evolved by the dissolution of 25 grams of sodium hydroxide? I know how much heat I have for 1 mole. I know how many moles I have. So let's figure out the Q. Number of moles times delta H of solution. 0.625 moles times negative 45 kilojoules per mole. This is negative 28 kilojoules. I'm running out of space here. Or negative 28,000 joules of heat. So for that amount of sodium hydroxide, 28,000 joules of heat is released. But that still has not answered our question. My change in temperature is 75 degrees C. Where did I get that? Let's look. How much solvent could how much solution could be heated to boiling by the heat evolved by the dissolution of 25 grams? For the solution, assume a heat capacity of 4 joules per gram degree C. An initial temperature, 25 degrees C, a boiling point of 100, and a density of 101.5 grams per ml. So my change in temperature, 75 degrees C, is going from that 25 up to that 100. I know Q equals MCAT. I learned that in Chem 1. So I know my delta T, I know my Q, I know my C. I can find my M. My Q I just found is negative 28,000 joules, but again, it's losing that much. So from the system's perspective of losing it, I'm going to make the value positive here because it is looking at the mass and we are measuring the surroundings. Okay. Remember system versus surroundings. My specific heat is 4.0 joules per gram degrees C. And my temperature is 75 degrees C. That should be zero point 0. This is at the 0 decimal places Here, they're both precise to the first decimal place, so that's be 75.0. Overall, this gives me 94 grams. Still not quite done, but that's telling me that if I was to gain 28,000 joules of heat and raise the temperature 75 degrees C with a specific heat of 4 joules per gram for every temperature, for every degree raised, that would be 94 grams of sodium hydroxide. So, how much solution could be heated? Well, we know the density of the solution. We're really close to being done. I've got 94 grams. 1 mil of the solution weighs 1.05 grams, 89 mils. So, in this question, how much solution can be heated to boiling by the heat involved with a dissolution of 25 grams of sodium hydroxide? 89 mils. 89 mils could actually be heated up. Number 15, the density of 20% of a 20% aqueous magnesium sulfate solution is 1.220 grams per mil. What is the molarity of this solution? Well, what do we know? What do we want to know? We know that we've got 20%. We know that it's aqueous. We know it's magnesium sulfate. We know the density, and we know what we're trying to find. Aqueous means water. Magnesium sulfate. Well, if I was doing if I was doing colligative properties, I would care. There'd be a Van 't Hoff factor of 2, but I don't much care about that. I don't need that here. It doesn't specifically say it percent by mass, but it should theoretically say that, because that's what we're going to solve it as, this percent by mass. We're going to say, okay, we have a 20% aqueous solution, so we're going to assume 100 grams of solution. Why did we do that? Well, because it tells me it's a percentage of it to be magnesium sulfate. And when we have a percentage, the easiest thing to do is assume 100 grams. It makes your math much, much easier. So how many moles of magnesium sulfate do I have? Well, if I have a 100-gram solution, 20 of those grams are magnesium sulfate. You guys need to show the math on this when you guys are showing this in assessments. Again, converting to moles, 1 mole of magnesium sulfate weighs 120.4 grams of magnesium sulfate. Magnesium is 24.31 grams per mole, sulfur is 32.07 grams per mole, 4 oxygens at 16 grams per mole each. That is 120.4 grams for 1 mole of magnesium sulfate, giving me 0.166 moles of magnesium sulfate. Not quite done. I do want molarity, which means I need the volume of the entire solution. So number of liters of solution. If I've got 100 grams, I'm going to use the density, 1 mil of solution to 1.220 grams of solution. That's going to give me milliliters. I'm then going to convert to liters. And I see I have 0.08197, 4 sig figs of 100 there, liters of solution. And why did I keep the 100 to the first decimal place? Because of the 20%. Now when I find my molarity here, 0. Sorry, 0.166 moles of the magnesium sulfate for every 0.08197 liters of solution. 2.03 molar magnesium sulfate. So when I had a 20, okay, what about number 16? Seawater has a density of 1.025 grams per mil and is typically 3%, 3.00 for sig figs, percent sodium chloride by mass. What is the molarity and molality of seawater? Okay, well, I've got a density here. Typically 3% sodium chloride by mass. I want molarity and molality. I have percent by mass, so I'm going to assume 100 grams of solution. Notice how I wrote that out to 2 decimal places for the zero? That's because of the 3.00. I'm just going to match that to whatever the value it was given. If I do that, though, that means I have 3 grams of NaCl and 97 grams of H2O. Go ahead and find the number of moles of NaCl. Show your work. 3 grams of NaCl converted to moles is 0.0513 moles of NaCl. I can pretty quickly find my molarity now. Or sorry, my molality. Molality. I have to find. I have to figure out the liters of solution in just a sec. My molality is 0.0513 moles of NaCl divided by 0.09700 grams of the solvent or water, whichever. I don't really care what you write there, as long as it's one of those two words. 0.529 molal NaCl. So I've got the molality down. Now I just need to work on the molarity. So I have a 100-gram solution. I'm going to convert with density. 1 mil divided by 1.025 grams of solution gives me 97.56 milliliters of solution. So again, for sig fig purposes, I use 100.00 here, but my density had 4 sig figs, which limited my final answer to 4 sig figs. So my molarity, 0.0513 moles of NaCl divided by 0.09756 liters of solution gives me 0.526 molar. So I can see that the concentrations are really similar from molarity to molality. Again, that's really common when the solutions are dilute, when they have a dilute concentration. It's really common for molarity and molality to be very similar or the same. They differ more when you have a bigger difference in a more concentrated solution. Let's see what's next. Let me get to the next photo. Okay. The equilibrium concentration of oxygen and water at 25 degrees C, which is in contact with air at 1 atmosphere pressure, is 8.5 times 10 negative third grams per liter. What will happen to the oxygen concentration in this if this water is moved to an elevation such as Denver, where the air pressure is 0.90 atmospheres? Will oxygen escape from the water until its concentration reaches 7.7 times 10 negative third grams per liter? Will more oxygen dissolve until the concentration reaches 9.5 times 10 to the negative third grams per liter? Will no change occur so as long as the percent oxygen in the air remains constant? Or will the only variable which matters be temperature? So assuming the temperature does not change, the concentration of oxygen will not change. This is looking at that idea of Henry's law, which is looking at solubility of gases based on the Henry's constant. So that equation, again, S is equal to KH times P. S being your solubility, KH being Henry's constant, and P being the pressure. We are told that, let's see where, I forgot where I'm at. 1 atmosphere of pressure and 8.5 times 10 negative third. We are then going to move this to this. Under the first set of conditions, my solubility is 8.5 times 10 negative third grams per liter. I have no idea what Henry's constant is, but I know that my pressure is 1 atmosphere. Why do I care about this? Well, because I can solve for that. That makes life real convenient here. My Henry's law constant will be 8.5 times 10 negative third grams per liter atmosphere. Now I'm going to use that equation again, plugging in my new pressure and solving for my solubility. So the solubility under the new set of conditions, 8.5 times 10 to the negative third grams per liter atmosphere, 0.90 atmosphere. My solubility is 7.7 times 10 to the negative third grams per liter. So I know my answer. Under that lower pressure system, the zero point 0.9 atmospheres of pressure, my solubility is 7.7 times 10 to the negative third. So the oxygen will escape from that water until it reaches its new solubility level, 7.7 times 10 to the negative third. Again, the first set of conditions allowed me to solve for for Henry's constant, Henry's law constant. The second, and then I just did the equation a second time to figure out the actual concentration that I would need. What about number 18? Let's see. We're definitely going to need some space here. The partial pressure of CO2, okay, so the partial pressure of CO2 in air is approximately 4.0 times 10 negative 4 atmosphere, okay? The solubility of CO2 in water under those conditions is 1.3 times 10 negative 5, okay? What is the solubility of CO2 in water when the partial pressure of CO2 is 1? I have no idea. Let's figure it out. So my solubility of my gas is equal to Henry's constant times the pressure of my gas. I am told that under the first set of conditions that the solubility is 1.3 times 10 negative 5 molar. I've got Henry's constant, and that is under a pressure of 4.0 times 10 negative 4 atmosphere. I solve for Henry's constant, and I get a value 0.0325. My sig figs are actually right here. Molar per atmosphere. Now I'm going to plug those in under the new set of conditions. My solubility of my gas, 0.0325 molar per atmosphere times 1.0 atmospheres gives me 0.033 molar. So the solubility of CO2 in water when the partial pressure is increased to 1 is 0.033 molar. That shouldn't surprise us too much. Under really low, relatively speaking, a much lower pressure compared to 1, my solubility is not the best. Under higher pressure condition, I have a higher solubility, which completely backs up everything we've learned about the gases and solubility of gases in water, in liquids. Excuse me, how they vary with pressure. Okay, let's look at number 19. The vapor pressure of pure water at 25 degrees C is 23.8 torr. Determine the vapor pressure of a solution containing 35 grams of urea, a non-volatile non-electrolyte dissolved in 75 grams of water. Okay, again, the reason we care about these things, why do we care that it's non-volatile? We care that it's non-volatile because that means that water is the only thing contributing to the actual vapor pressure. I don't have to play this game of multiple things contributing. It's just simply water that's contributing. And non-electrolyte. Why do I care that it's non-electrolyte? Because that means my I value is 1. And that makes my math easier because that means that my mole fraction for that species will not be multiplied by anything. It will just be 1. In order to find this, my pressure in my solution is going to be equal to the mole fraction of water times the pure vapor pressure of water. To find the mole fraction, I'm going to need the number of moles of water divided by the total moles of the system. So, and this one, I mean, in outside of class, you guys can look this up. If this was on a quiz or an exam, I would give you the formula for urea. But moles, urea, I have 35 grams, and urea has a mass of 60.06 grams per mole. So I have 0.583 moles of urea. Number of moles of water, 75.0 grams. Sorry, 75.0 grams going into moles of water gives me 4.16 moles of water. Again, if urea had a different I value, this is where I'm multiplying it by that I value, okay? I'm doing it right here. It stays the same because I is equal to 1, so I still keep 0.583 moles of urea. But if I had a different I value there, that's where I would multiply it. My mole fraction of water, 4.16 moles of water, divided by the 4.16 moles, plus the 0.583 moles, again from water and urea. This gives me a mole fraction of 0.877. Now I can go ahead and plug that into the equation for the pressure of the solution. So my pressure of my solution, 0.877, times the pure vapor pressure, which is 23.8. Don't forget your units there. And I get an answer of 20.94. And some students really want to convert to atmosphere because we convert to atmosphere a lot. I get it. But if you don't have to convert, don't. And in this one, you don't have to. So don't do it. You're just likely to waste time or make a mistake or both. It's not worth it. It doesn't tell you what the units have to be. So just leave them whatever's easiest. What about number 20? A solution is prepared by mixing 0.200 moles of acetone with 0.600 moles of ethyl acetate. At 30 degrees C, the vapor pressure of pure acetone is this, and the vapor pressure of pure ethyl acetate is this. Assuming this behaves in an ideal solution, what is the total vapor pressure of the solution at 30 degrees C? Okay. It's one of those ones where you have to pay attention to both. So I've got 0.022 moles of acetone, which has a vapor pressure of 285 torr, and I've got 0.600 moles of ethyl acetate, which has a vapor pressure of 118 torr. So the total pressure is just the individuals times their mole fraction. Pressure of the solution is equal to the mole fraction of acetone times the partial pure vapor pressure of acetone plus the mole fraction of, what am I using? Ethyl acetate times the partial pressure of ethyl acetate. I have to find those mole fractions, but again, the mole fraction of acetone is 0.200 moles for acetone divided by 0.800 moles total. The zero point 0.6 and the zero point 0.2 add up to 0.8. This gives me 0.250 for the mole fraction of acetone, which means that the ethyl acetate has to be the remainder. It's the only two things in the system. You can also check your math here if you'd like. The zero point 0.6 moles of ethyl acetate divided by 0.8 moles total. That gives me the mole fraction of ethyl acetate as well. Just reading that as EA for simplicity. We'll plug those into the equation up here. The of my solution is equal to 0.250 for the acetone, and that is times 285 torr, plus 0.750 for the ethyl acetate, times 118 torr. The total pressure of the solution, 160 torr. So again, that one works very similarly to what you guys learned in Chem 1. It's still an application of Dalton's law. It's just a little bit different because we're dealing with, just vapor pressures here. What's next? Number 21. Assuming complete dissociation, which of the following solutions would have the lowest vapor pressure? They all have the same concentration, so that part's cool. Makes my life easier. I don't have to deal with multiplying them by their Van Hoff factor. I could just look at the Van Hoff factor now. If I've got magnesium chloride, my Van Hoff factor will be 3. It splits up into magnesium ions and 2 moles of chloride ions, therefore 3 for the Van Hoff. Glucose is a non-electrolyte. Its I value equals 1. Sodium nitrate is a salt. It splits up into 2 things, sodium ions and nitrate ions, and its Van Hoff factor is 2. Sodium bromide, also 2, splits up into sodium ions and bromide ions, and then pure water, non-electrolyte, and a value of 1. And the molality of pure water is very, very high. It's pure. So I'm looking for the thing that's going to have the lowest vapor pressure. Oh, only one of these is not like the other. So it's kind of an easy guess if I really didn't know what I was doing. I'd be like, well, 1 and 1 are kind of hard to tell. 2 and 2 are kind of hard to tell. But this is 3. Something going on with that 3. So, like, if I had to guess, I'd probably guess this one. And that'd be good because I'd be guessing correctly. Let's talk about why. Again, what is vapor pressure? Vapor pressure is the pressure of the vapor. Okay, that wasn't very helpful. I have a glass of water. Some of those water molecules that are in that glass have enough energy to escape the solution. They escape by going into the vapor phase. Vapor means that those water molecules are gas, but at a temperature that the water is not boiling. So they're actually escaping into the gas phase when I wouldn't expect them to based on boiling points. The more particles that escape that solution, the higher my vapor pressure because they're in a vapor, meaning they are a vapor, but they're in the gas phase, and gases exert a pressure. So vapor pressure is due to those particles that have escaped exerting a pressure back down. The lowest vapor pressure is going to be the one that has the fewest particles escape. On letters B and D, or sorry, B and E down here, my Van Hoff factor is only 1. That means that let's just treat it as a 1. Let's say we have a 1 molecule that holds 1 water molecule behind. Okay, comparison thing. I have 1 water molecule. Let's say I've got 10 water molecules trying to escape. That means that this is holding back 1 of them. So now only 9 were able to escape. Under C and D, I have a Van Hoff factor of 2. That means each one of these, because they were the same concentration, okay, otherwise you have to multiply it by concentration as well and figure out the numbers. But because they have these same Van Hoff factor, each particle is holding back 1 water molecule. That means that 2 water molecules are being held back per solution. Therefore, 8 molecules have been able to escape. Okay? That's still lower than 9. Then I look here and I see a Van Hoff factor of 3. So that means that 3 water molecules are being held behind, only 7 were able to escape. This overall will have the lowest vapor pressure because it has the fewest molecules being able to escape. Let's look at number 22. Just to let you know that giant circle right there, that is just so that I remember on future editions of these PowerPoints to move that negative sign because it's in a really bad spot. So it's just to warn me to move that negative sign down here. Okay, so that we can recognize it's a negative sign down here. The freezing point of pure carbon tetrachloride is negative 22.3 degrees C, and its Kf value is 29.8 degrees C per mol. What is the freezing point of a solution containing 5 grams of naphthalene, C10H8, a non-electrolyte, dissolved in 60 grams of chloroform? Okay, well, let's see what we got. We are trying to find, or sorry, we are told the freezing point of, I'm doing great here. I'm hitting the back button too many times. I'm sorry. We are told the freezing point is negative 22.3. We are told the Kf is 29.88. We want to know the freezing point of the solution. We know that it has 5 grams of naphthalene. We're given the molar mass. We're told it's an electrolyte. And we're told the mass of the solvent. So we got a lot of information here. That's actually quite helpful. I know that in order to solve this, I'm going to have to use the freezing point equation. Delta TF is equal to KF times M times I. I know my KF is 29.8 degrees C per mole. I know my Van Hoff factor is 1 because it's a non-electrolyte. I don't know my delta T yet, but I can figure out my molality actually, because I know what's in here. My molality is my moles of solute over kilograms of solvent. 5 grams of naphthalene converted to moles. 1 mole of naphthalene weighs 128.16 grams. Carbon is 12.01 each, and there's 10 of them. Hydrogen is 1.008, and there's 8 of them. So 5 grams times 1 mole of C10H8 divided by 128.16 grams of C10H8 gives me 0.0390. And that is moles. I need to divide this by my solvent in kilograms. I'm told I use 60 grams, so 0.06000 for sig fig purposes. Let's see, oh, two zeros, 00 for sig fig purposes, kilograms of the solvent. This gives me a molality of 0.650 molal. My delta T is what I'm trying to find. So now that I know this, 0.650 molal, I can plug that in here. And what I get for this change in temperature is 19.4 degrees C. But again, that's not my final answer. My final answer is freezing point depression. So it is depressing the freezing point. My freezing point started at negative 22.3 degrees C. From that, I'm removing another, I forgot where I wrote, there it is, 19.4 degrees C. So I'm removing another 19.4 degrees C. It's already cold. I'm just making it colder. The final temperature here, negative 41.7 degrees C. Number 23. 5 grams of sodium chloride were dissolved in 100 grams of water. What is the boiling point of the solution at 1 atmosphere pressure, assuming complete dissociation? Okay, what do we got? Well, let's start with our 5 grams of sodium chloride. How many moles is that? I know 1 mole of sodium chloride weighs 58.44 grams. So therefore, if I do the math here, I'm going to get 0.0856 moles of NaCl. I need molality. I'm told how much dissolved in, but I need molality to solve the question. So to find more boiling points, I'm going to have the molality. Molality is going to be 0.0856 moles of the NaCl. 100 grams of solvent is the same as 0.100 kilograms of solvent. Gives me 0.856 molal. Delta TB is equal to TB times M times I. For water, again, I will give this to you. For water, your delta TB is 0.512. Your molality you just found is 0.856. Your Van Hoff factor is 2, because again, sodium chloride splits up into 2 things. My delta TB, 0.873 degrees Celsius. You're following around with the student notes. I have this labeled here as sig figs here, but that's because when I actually looked up the boiling point elevation constant, I just wrote it down to 2 sig figs, not 3. So pick your battles there. Let's see. That is not my true boiling point. I know this boils at 100 degrees Celsius. Because of my sig figs here, again, because I wrote 0.512 here, this actually has 3 sig figs here. If you're looking at my notes, I wrote 0.51, leaves me with 2 sig figs. 0.0873 degrees C gives me 100. 0.873 degrees C. So by adding 5 grams of sodium chloride to 100 grams of water, the boiling point has not gone up very much. It's gone up less than a degree. It's gone up 0.87 degrees. Assuming complete dissociation, which of the aqueous solutions below has the lowest freezing point? So they all have a different molarity and they all have a different I value. So go ahead and figure out your I values first. Again, I is your Van Hoff factor. This splits up into 3 sodiums and 1 phosphate. My value here is 4. This splits up into 1 potassium and 1 chloride. My I value is 2. This splits up into 1 calcium and 1 chloride. My I value is 3. This splits up into 2 things. My I value is 2, and non-electrolyte means that my I value is 1. Now, though, I'm going to multiply that by the molality I got for each species, because again, molality tells you the number of moles of things. So this is the number of moles I have of something if I had 1 liter of solution. This is how many things I have. So I need to multiply that molality by 4 to get the actual, like, reasonable answer here. This gives me 0.80. This one gives me 0.44. This one gives me 0.075. This one gives me 0.60. And this one, because my I is 1, gives me 0.40. I don't know if you can read that. I do apologize, you guys. I'm getting pretty tired. And so if I'm not focused, I do apologize. Just trying to get these done. Um, I looked for, okay, so I forgot what I'm solving for, lowest freezing point. So it is called freezing point depression. So which one's going to have the greatest effect on my solution? That's going to be this one because it's got the greatest value difference here. This is going to lead to the lowest freezing point. Now, if I had highest freezing point, I would have picked the lowest value because again, it's freezing point depression, but it does say lowest freezing point. So I'm going to go with the one that has the true or has a lowest freezing point, and that will be comparative. I mean, others may freeze below water, but this one is going to be the lowest to freeze the water because of the zero point 0.8 factor, um, not just 0.44, 0.75, etc. 0.20 molar solution of magnesium sulfate has an observed osmotic pressure of 78 atmospheres at 25 degrees C. Determine the observed Van Hoff factor I for this experiment. Okay, my osmotic pressure is pi is equal to m RTI. I'm told the osmotic pressure is 7.8 atmospheres. I know my concentration is 0.20 molar. I know my gas constant is 0.08206. Liter atmosphere per mole K. I know my temperature is 25 degrees C, which is 298. And I'm trying to figure out what I is. So I is what I'm solving for. When I solve that equation out, I'm going to get an I value of 1.6. Theoretically, I would expect magnesium sulfate to have an I value of 2. But again, that's under infinite dilution conditions. That's when none of those particles are interacting with each other. So the fact that I've got an I value of 1.6, not surprising at all. Just means that some of the magnesium ions are not separating from some of the sulfate ions. See, number 26, the osmotic pressure of human blood is 7.6 atmospheres at 37 degrees C, which is normal body temperature. What mass of glucose, C6H12O6, molar mass 180.2 grams per mole, is required to make 1 liter of aqueous solution for intravenous feeding if the solution must have the same osmotic pressure as blood at the at body temperature 37 degrees C? I guess we're using osmotic pressure again. I equals MRT I. I know that it needs to match, so I've got 7.6 atmospheres. I don't know what the molarity is. Actually, that's what I'm going to be trying to find because I'm going to use that to find the mass of glucose. I know my gas constant is 0.08206 liter atmosphere per mole K. I know my temperature here is 310 Kelvin because I converted that to Kelvin. And I know that glucose is a non-electrolyte, so I is going to be equal to 1. Solve for the molarity here, and I get a molarity of 0.299 molar. So in order to get that pressure, I'm going to need 0.299 molar. I'm going to use that to find the grams. Maybe I should write the right formula. I'm sorry, you guys. I'm just really tired. I know that it's 0.299 moles per 1 liter of solution. I know that we use 1 liter, or I assumed, not know, I'm assuming we're using 1 liter to undo this. We've got 180.2 grams for every 1 mole. So I've got 54 grams of C6H12O6. Basically, to bring the pressure of this up to the same as human blood, I would need to add 54 grams of glucose to it. Number 27, a solution was prepared by dissolving 1 gram of an unknown non-electrolyte in 50 grams of carbon tetrachloride. The freezing point of the solution was found to be negative 28.4 degrees C. What is the molar mass of this unknown solute? And then it tells me the freezing point of chloroform is this, and Kf for carbon tetrachloride is 29.8 degrees C per mole. So I know I'm doing freezing point, so delta T is equal to Kf times M times I. I know that the solution is freezing at negative 28.4, but the pure solution is 29.8. I'm sorry, I really should just stop making a video, but I really want to try to get this done for you guys. I'm so tired. Um, negative 22.3 degrees Celsius is the actual temperature um, of the pure solvent. So the 29.8 is your freezing point depression constant. So for temperature change, I have negative 28.4 minus negative 22.3. The overall change in temperature there is 6.1 degrees Celsius. My KF value, 29.8 degrees C per mole. Times my molality, which I'm trying to find, times my Van Hoff factor. I have a non-electrolyte, so my Van Hoff factor will be a value of 1. Solve for molality, and I get a value of 0.205 molal. But remember, it also told me that I used 50 grams of carbon tetrachloride. So I can use that information. I can say number of moles. I apologize if you're hearing all these noises. I have way too many cats, and all they want to do is just mess with my stuff. 0.205 molal and 0.5000 kilograms of solvent. Gives me 0.0103 moles. I now know 1 gram of the unknown, caused this freezing point depression of 6.1 degrees C. And I know the moles that correlated to that grams. My molar mass, 1.000 grams, divided by 0.0103 moles, gives me 97.1 grams per mole. Sorry if you heard that as well. I'm used to having one cat, and kittens throw a wrench in things. Okay, let's see, number 28. Where are we? The density of a 0.438 molar solution of potassium chromate at 29 or 298 Kelvin is 1.063 grams per mil. Calculate the vapor pressure of water above the solution. The vapor pressure of pure water at this temperature is 0.0313 atmospheres. Assume complete dissociation of the solute. Okay. I'm not told much. I mean, I'm told some. Like, I have a density of solution, I have a molarity of solution. Trying to get to vapor pressure. And I have an initial I have an initial pressure. Or sorry, yeah, I have vapor pressure at the I have vapor pressure at this temperature. Okay. I'm going to move this over. I'm just gonna shove it there. I'm going to assume 1,000 mils of solution. Why 1,000? I'm given a molarity. That would mean I have 0.438 moles of potassium dichromate. Or chromate, not dichromate. I know that if I look at potassium dichromate, that's going to split into 2 potassium ions and 1 chromate ion. So I know my I value is 3. I know my mass of my solution. Let's see. If I assume 1,000 mils, which I did up here, and use that density, that gets me density and gets me 1063 grams of the solution. I really need the mass of the solvent here. I need to figure out how many moles I have of it. Mass of solvent is 1063 grams minus the mass of my solute. If I convert this to moles, sorry, if I convert this moles to grams, I'm going to get 85.1 grams of the K2C2 K2C2 CR2O4. So 1063 minus 85.1 grams gives me 977, sig figs are here, 0.9 grams of H2O or whatever solvent. I'm also going to figure out the moles of that. Converting that to moles, that gives me 54.3 moles of water. Why do I care? I need my mole fraction because I'm doing vapor pressure. My mole fraction of water is 54.3 moles of water divided by 54.3 moles of water plus 0.438 moles, but I'm multiplying this by a value of 3 because, again, my Van Hoff factor has a value of 3. So I need to multiply those moles by that value because I have that many more particles. A mole is telling you how many particles you have. Mine didn't stay in one set of particles. Mine split up into multiple particles. This gives me a mole fraction of 0.977. So my pressure of my solution is 0.977 times 0.0313. Overall, my answer, 0.0306 atmospheres. I don't truly care what unit you put it in. I left it in atmosphere because it was an atmosphere to start. We're nearing the end. Yeah, we're getting there. Okay. Yes. Okay. 29. The vapor osmotic pressure of a solution containing 2.10 grams of an unknown compound dissolved in 175 mils of a solution at 25 degrees C is 1.93 atmosphere. The combustion of 24.02 grams of the unknown compound produced 28.16 grams of CO2 and 8.64 grams of water. What is the molecular formula of the compound, which contains only carbons, hydrogens, and oxygens? I thought this question was kind of cool. Definitely cumulative. So I've got osmotic pressure, which means I know I'm going to be using pi equals MRTI. For this, let's see, I forgot what I read already. Osmotic pressure, 2.10 grams of an unknown compound. It's dissolved in 175 mils of a solution, 25 degrees C, and it's this much pressure. The combustion of 24.02 grams of the unknown product produced 28.16 grams of CO2 and 8.64 grams of H2O. And I want to know the formula. Well, it doesn't tell me anything, so I'm going to have to assume that Van Hoff factor is 1. Doesn't give me a clue that it's not, and I'd have to have something that it would not be. Now, it does say at the end, what is the molecular formula of the compound, which contains only carbons, hydrogen, and oxygens? That doesn't imply the I value is 1, because just carbons, hydrogen, and oxygens imply that it is really a molecular compound. So we're going to assume that it didn't lose anything along the way, and it really is just a molecular compound with everything collected. I've got 1.93 atmospheres. Trying to solve for molarity. 0.08206 liter atmosphere mole K times the temperature. My temperature for this is 24.02, which becomes 298.2. My molarity here, 0.0789. So 1 liter. When I want to find my number of moles, because I know how much unknown compound was dissolved in, I'm going to take this value up here, multiply it by 0.175. Sorry. 0.175 liters gives me 0.0138 moles of the sample. So I've got 0.138 moles of the sample. I'm going to go ahead and figure out how many moles of carbon, hydrogen, oxygen I have here. Remember, all of that CO2 that's mentioned here came from carbon. So 28.16 moles of CO2. I know for every 1 mole of CO2, it's 44.01 grams. And I know that 1 mole of carbon is contained in every 1 mole of CO2. This gives me 0.640 moles of CO2, or sorry, moles of carbon in the sample. So I will need in a sec to figure out oxygen. I also realize that 0.640 moles is the same as 7.6 grams. Do the same thing. Number of moles of hydrogen. 8.64 grams of water. 18.02 grams of water. 2 moles of hydrogen for every 1 mole of water. 0.959 moles of H, which gave me 0.967 sorry, 967 grams of hydrogen. But I can use that to find the grams of oxygen because I know that the entire sample that was combusted was 2.10 grams. I know conservation of mass, so I know that my grams of oxygen have to be equal to the difference. Okay, there it is, 24.02. The solution contained 2.10, but the sample that was actually burned was 24.02 grams. So 24.02 grams sample minus 7.60 grams of carbon minus 0.967 grams of hydrogen. This gives me 152 grams. Sorry. I really do apologize, you guys. I'm just incredibly tired. Um, this gives me 15.37 grams of oxygen, which is the same as if I convert it over 0.961 moles of oxygen. So carbon has 0.640 moles. Oxygen has 0.961 moles. Hydrogen has 0.959 moles. We divide all by the smallest numbers, divide all by carbon's number. This gets me a 1. Oxygen gets me a 1.5. Hydrogen gets me a 1.5. We can't have fractions. We multiply them all by the least common multiplet. C2H3O3. Now, this question, though, tells me that hold on. What's the molecular formula? Uh, it's missing something. I forgot to put the last piece of the question on here, I guess. Because I know that the compound has to be twice the molar mass of this. I know the molar mass of this is 75 grams per mole. It has to be twice that. So the actual compound is C4H6O6. If I gave you a question like this, most likely I would just say like your mass is between this range and this range. Usually the question will say something like the mass is between the range of like 125 and 175, and you would calculate it out to be 75 and realize that's too small, so you've got to double the mass. Number 30 is a doozy. 30. A solution of 75 grams of benzene, C6H6, and 75 grams of toluene, C7H8, has a total vapor pressure of 80.9 millimeters of mercury at 303 Kelvin. Another solution of 100 grams of benzene and 50 grams of toluene has a total vapor pressure of 93.9 millimeters of mercury at this temperature. Find the vapor pressure of pure benzene and pure toluene at 303 K. Okay. I know they're both volatile. So I know that my pressure of my solution 1 is 80.9 millimeters of mercury. I know that equals a mole fraction of C6H6 times the partial pressure of C6H6 under condition 1 plus the mole fraction of C7H8 times the partial pressure of C7H8 under condition 1. I know my mole fraction, 75.0 grams, C6H6, or calculate that out, the molar mass is 78.11. This gives me a mole fraction of 0.960 moles. If I figure out it gives me moles of this, of C6H6. If I figure out the number of moles, I'll do mole fraction in a sec. Number of moles of 75 grams of C7H8 is 0.184 moles. The mole fraction of this one is 0.541, so the mole fraction of the other species is the remainder to get up to 1 is 0.459. Haven't gotten close to answering the question yet, but at least I know the mole fraction of each species. So I can plug that in to the equation above. I know my mole fraction here is actually 0.541. I know my mole fraction here is actually 0.459. So all the partial pressures, but at least I know that. What I'm going to do is I'm going to rearrange this equation specifically to solve for this. Okay, so I'm algebraically rearrange the equation. The partial pressure of C6H6 is equal to 80.9 millimeters of mercury minus 0.459. I'm not going to run out of room up there. 1 second. Come right down here. Partial pressure, I'll zoom out in a sec. C6H6 is equal to 80.9 millimeters of mercury minus 0.459 times the partial pressure of C7H8 divided by 0.541. Why did I do that? Because I'm going to have two equations soon, and I don't have two unknowns, and I need to find a way to substitute. So again, what I did was solve for this in the equation. Okay, I isolated that here. I'm going to do the same thing for the other example, for the other set of conditions in here. Because this was for the first set of conditions, where there's 75 grams of each. But it's also telling me if I have 100 grams and 50 grams of benzene and toluene respectively, what the vapor pressure of that solution is. So I'm going to take advantage of that as well. Doing what we just did, P of my solution 2 is 93.9 millimeters of mercury. This equals the mole fraction of benzene times the partial pressure of benzene plus the mole fraction of toluene times the partial pressure of toluene. So just like before, I'm going to figure out the moles the mole fraction of each species, okay? And again, this is based on now I've got, previously I had 75 grams of each, now I've got 100 and then 50. What I find here is my mole fraction of C6H6 is 0.702. How did I find that? I use that 100 grams of benzene, convert that to moles of benzene, and I divide it by the total moles of the system. So the moles of the benzene and the moles of the toluene. That also means that my moles of toluene is equal to 0.298 because it's the two added together have to equal to 1 for the two components of the system. So 93.9, I'm going to put it up here, 93.9 millimeters of mercury. This substitutes into here, and this substitutes into here. So I've got the mole fraction of each species now. But I also have, if you remember, this. I have the partial pressure of benzene right here. I can plug this thing into my equation here and solve it algebraically. And that's what I'm going to do. Okay. Partial pressure, C6H6, I solved for earlier. That's going to equal 80.9 millimeters of mercury minus 0.459 partial pressure of C7H8 divided by 0.541 equals 149 millimeters of mercury minus 0.848 partial pressure of C7H8. I'm going to need to go ahead and solve this thing algebraically. It's going to be fun. It's not actually that bad, but let me see if I can. Sorry, my hand is really starting to, or my wrist is really starting to hurt. 0.702 times 149 millimeters of mercury minus 0.848, which is the partial vapor pressure of pure toluene. So basically plug it into here kind of thing, okay? Plus 0.298 Partial pressure C7H8, 93.9 millimeters mercury. I get 105 millimeters mercury minus 0.9595 partial pressure C7H8 plus 0.298 partial pressure of C7H8 is equal to 93.9 millimeters of mercury. I get 0.297 partial pressure of C7H8 is equal to negative 11.1 millimeters of mercury. I get the vapor pressure of C7H8, or also known as toluene, 37.4 millimeters of mercury. Now that I have that, I can plug it back into one of the earlier equations. 93.9 millimeters of mercury is 0.702 times the vapor pressure of pure benzene plus 0.298 times 37.4 millimeters of mercury. Partial pressure C6H6 is 118 millimeters of mercury. I realize it's a lot of work on this slide. Lots going on in here. But basically, at the end of it all, partial pressure of, sorry, I can't write on low screens like that. Partial pressure of benzene, C6H6, is 118 millimeters of mercury. And the partial pressure of toluene, C7H8, is 37.4 millimeters of mercury. Again, if you didn't follow what I did, I suggest trying this yourself, but I solved for the mole fraction of each species individually. I then plugged them into the overall equation of what it would look like, and I rearranged the equation isolated for the partial pressure of one of them, and I just substituted that isolation in, which was, again, this equation here, I substituted in later on when we got to the, when we wrote up the second equation. Our last one. A metal M reacts with chlorine to form a salt that can be represented by MCl3. 15.83 grams of this salt was dissolved in 25.02 grams of water. The vapor pressure of the resulting solution was measured to be 18.54 torr. Assume complete dissociation of the salt. What is the identity of the metal? Get to the right slide. Okay. So I know I've got a metal, M. I know it reacts with chlorine to form a salt to be represented by MCl3. So I know my I value. I know I has to be equal to 4. So I've got one metal and 3 chlorines. I know I've got 15.83 grams of this salt dissolved in 25.02 grams of water. So I know what my solvent is. I know the vapor pressure of the resulting solution was measured to be 18.54 torr. I'm assuming complete dissociation, so I'm assuming that 4 Van Hoff factor of 4. And I really want to know identity. And when I want to know identity, that means what is my molar mass? How many grams do I have to how many moles do I have? First step, I'm going to figure out the vapor pressure of the solution. It tells me the vapor pressure of the overall solution is 18.54. Remember the equation here. The vapor pressure of the solution is equal to the mole fraction of the volatile species times the partial pressure of the volatile species at that temperature. The salt is not volatile. Salt doesn't just evaporate away, but water will. So the water is volatile species here. This is 18.54 torr, and this equals the mole fraction of water times the vapor pressure of water at this temperature, which again on a quiz or exam I will give to you. On here, you will have to recognize that you have to look that up if I do not give it to you. This leaves me with a mole fraction though, so that's what I'm going to solve for. It leaves me with a mole fraction of 0.7803. I know my mole fraction. I know my Van Hoff factor. So the second thing I'm going to do here, I know my mole fraction should be my number of moles of water divided by the total moles of the system. So the moles of water plus the moles of my salt times 4. Because again, this is the number of moles of particles in solution. The metal I have, the MCl3, is splitting up into 4 things. So it's multiplying that mole by 4. Substitute in what I know. I know my mole fraction is 0.7803. I know my number of moles of water is 1.388. How do I know that? Because I know how many grams of water I've got. I just converted that 25.02 into moles. So 1.388 moles of water divided by 1.388 moles plus X times 4. I don't know the moles. That's what I'm trying to find, is the moles of that unknown. Solve this algebraically. 0.7803 times 1.388 plus 4x equals 1.388. 1.083 plus 3.121x equals 1.388. Solve for x. X is equal to 0.0977. But what does x represent? X represents the number of moles of MCl3, which is what I need because I want to solve for molar mass. So again, my molar mass, I'm told that the salt itself is 15.83 grams. I just found the moles of the salt to be 0.0977 moles, and that gives me 162 grams per mole. But I'm not quite done. I can't just look at the table and say the metal with 162 grams per mole, because this is the molar mass of the entire salt. Three chlorines are trapped in this wet mass. So minus 3 times 35.45 grams per mole gives me a molar mass of 55.65 grams per mole, which means my metal is iron. So the metal, what is the identity of the metal? Iron. Congratulations, you have finished the additional practice for Module 13.